Okay, imagine holding a material that in certain situations is literally harder than steel. You can stretch it out so it's thinner than a human hair, use it to beam light all the way across the globe, and yet, if you tap it just right, it shatters into a million pieces. Welcome to this explainer. Today, we are going to unpack how a handful of ordinary dirt transforms into what is arguably one of humanity's absolute greatest technological achievements, glass.
Here is a quick look at today's agenda. We're going to start with the glass paradox, then look at how it's forged in fire, dive into some incredible modern engineering, check out nature's very own glass factory, and finally, look at an unsolved atomic mystery. Let's dive right into Section 1, the glass paradox, or the origins of a contradiction.
I want to kick things off and immediately disrupt what you think you know by asking a pretty simple question. Is glass actually a solid? I mean, most of us would instantly just say yes, obviously. But the truth? It's way more complicated than that. We're going to definitively answer this by the end of the explainer, and honestly, the answer might completely change how you view the world around you.
Think about the extreme physical juxtaposition of this material for a second. It's wild. It can be engineered to be incredibly strong, withstanding just immense amounts of pressure. Or, like we mentioned, it can be stretched incredibly thin to carry all of our internet data across the ocean. But despite all of that high-tech, heavy-duty utility, it remains fragile enough that a simple tap can completely destroy it. It is a material entirely defined by its extremes.
But here is the ultimate paradox. This massive high-tech marvel begins its life as something completely mundane. Sand. Just sand. Now, to be fair, it's not exactly the sand you'd scoop up at your local beach. That stuff is full of shells and iron. To make glass, you need a highly pure, impurity-free version known as silica sand, which is packed with silicon dioxide. That right there is the foundational building block for literally everything, from the smartphone in your pocket to a billion-dollar space telescope.
Moving on to Section 2, forged in fire. This is where we look at the literal alchemy of glassmaking.
So to actually get pure silica to melt, you have to push temperatures to absolute extremes. Pure silica demands a melting point of around 1700 degrees Celsius. To put that into perspective, that is nearly as hot as molten lava. Melting pure silica all on its own consumes just a massive, enormous amount of energy, which, as you can imagine, historically made it really difficult to produce at any kind of scale.
So how did they do it? Well, ancient artisans actually figured out a brilliant chemical hack to make the process economical. By mixing the silica sand with soda ash, they realized they could drastically lower that crazy heat requirement. But there was a catch. Glass made just with soda ash will literally dissolve in water. Not great for a drinking cup, right? So they added limestone into the mix. That ensures the final product is durable and water-resistant. And it's crazy to think about, but this exact fundamental recipe has been quietly shaping human civilization for millennia.
And if you want to change what the final product looks like, it's all about tweaking the chemistry. You toss in some iron compounds, you get green glass, add cobalt, you get blue. But the most fascinating one, for sure, is red. Even just microscopic, tiny quantities of real, actual gold can be added to engineer an incredibly rich, ruby red glass. It's a technique that is still used in luxury glassmaking to this day.
Okay, so once your ingredients are perfectly blended and sent into those industrial furnaces running near 1600 degrees Celsius, the whole mixture turns into this intense, glowing orange liquid. But at this early stage, it's totally full of trapped bubbles. If you let it cool like that, the final product would be super weak and visually completely distorted. So it has to undergo a purification process called refining. Basically, they just hold it at those extreme temperatures so the bubbles naturally rise to the surface and escape, leaving behind a perfectly clear material.
Now, once it's refined, how do we actually get the perfectly flat windows we use every single day? Before the 1950s, making perfectly flat glass was painfully difficult and expensive. But then came an absolute game changer, the float glass process. Manufacturers literally take the molten glass and pour it directly onto a bath of molten tin. And because molten glass floats perfectly on liquid tin, kind of like oil floating on water, gravity just does all the heavy lifting. It spreads out into astonishingly smooth sheets that require basically zero polishing. It's pure genius.
And you know, the cooling phase is just as critical as the melting phase. If glass cools down too fast, internal stresses build up and the whole thing might just crack without warning. That's why we have annealed glass, which is cooled super gradually in a tunnel to carefully remove that internal stress. Compare that to tempered glass. For tempered glass, they reheat it and then blast it with air to cool it incredibly rapidly. That locks in surface compression, making the glass 4 to 5 times stronger. And the best part? When tempered glass finally does break, instead of forming deadly sharp shards, it safely shatters into thousands of tiny, dull, rounded pieces.
All right, Section 3, Engineering Superglass and its Modern Applications.
So, how are we using this today? Well, atomic-scale engineering of glass literally impacts our lives every single day. Take your car windshield. That's laminated glass, meaning it's actually two layers of glass bonded together with a hidden, transparent plastic layer. So if you're in a crash and it breaks, the shards stay safely glued to the plastic instead of flying everywhere. It saves lives. Then there's your smartphone screen. Those are immersed in molten potassium salts, where larger potassium ions squeeze in and replace smaller sodium ions on the surface, creating massive scratch resistance at the atomic level. Oh, and fiber optics? Those strands, thinner than a human hair, are powering our entire global internet by bouncing light along the core using total internal reflection.
Which brings us to Section 4, Nature's Glass Factory, where Earth does the manufacturing. Human engineering is absolutely remarkable, no doubt. But let's shift our perspective for a second, because nature has been running its own extreme glass factories for millennia, way before we ever built a furnace. When temperatures spike naturally, the Earth just creates its own glass. Lightning strikes in sandy deserts, they instantly melt the sand into these crazy, hollow, frozen lightning tubes called fulgurites. Meteor impacts hit the Earth with such enormous heat that they scatter mysterious green and black impact glass all over the landscape. And of course, volcanoes produce obsidian. That happens when lava cools so rapidly that crystals don't even have time to form. Ancient humans used obsidian for knives, and frankly, it's so incredibly sharp that some modern surgeons are even experimenting with it for scalpel blades.
But back in the human realm, we harness these extreme properties for the greater good. This material allows us to build ultra-stable space telescope mirrors that weigh tons but can tolerate absolutely zero distortion, allowing us to peer billions of light years out into the universe. Over in medicine, perfectly non-reactive glass lab equipment is absolutely crucial for creating vaccines and driving scientific discovery. And here's the beautiful part. Glass offers the unique benefit of endless recycling. A glass bottle can be melted down to become another glass bottle, over and over, essentially forever, without ever losing its quality. Plus, recycled glass melts faster than raw sand, dramatically reducing both energy consumption and carbon emissions. Finally, let's wrap up with Section 5, an unsolved mystery, the paradox at the atomic level.
Remember that question we asked at the very beginning? Is glass actually a solid? Well, here's the deal. Unlike perfectly ordered crystals, the atomic structure of glass is completely random. Everything is just frozen in place without a regular pattern. Because of this totally unorganized arrangement, scientists classify it as an amorphous solid. It completely defies the traditional boundaries of what we consider a standard solid material, and honestly, this exact definition continues to fuel fierce scientific debate today.
And talking about this brings us to a really famous misunderstanding. You've probably heard the trivia fact that old medieval cathedral windows are thicker at the bottom, because glass is actually a super slow-moving liquid that drips like honey over centuries. Well, modern research has completely busted this myth. The glass isn't flowing at all. Those old windows were simply manufactured unevenly by artisans using medieval techniques, and builders usually put the heavier, thicker end at the bottom for stability. But even though it definitely doesn't flow like a liquid, its atomic state remains fundamentally weird and different from almost every other common solid on Earth.
So there you have it. Glass has quietly shaped human civilization for over 5,000 years. The next time you look through a window, take a second to remember that you are looking right through a technological triumph born from ordinary sand and extreme fire that still holds secrets physicists cannot fully explain. It leaves us with a pretty provocative thought. If this everyday marvel still holds unsolved atomic mysteries, what other extraordinary magic is hiding in plain sight, just waiting to be understood?